Okay. You're twiddling with a few. Is it?
It is. It's
good.
water.
Good. Yeah. Okay. Well, it's 7:30-ish, so it's time to go. Welcome everyone to Royal Society Chemistry Belgium section. Tonight we're welcoming back to Brussels Professor Andrea Sella from University College London, and he's talk about strange ice. He last visited us in 2010, which is a remarkably long time ago, because it only feels like yesterday. When he talked to us, he gave us his zebra stripes talk, and we've been trying to get him back ever since. And but Bob made a recent intervention and secured his
emotional
presence.
blackmail.
in fact, but I wouldn't be at all surprised. But anyway, as we all should know, Andrea is a chemist and broadcaster based at University College London. And he's Professor of Inorganic Chemistry. His main research areas, it says here, are on rare earth metals, and collaborates with several research groups on hydrogen storage, carbon nitrides, and nanotube insertion chemistry. Yeah. And of course, he's also involved in numerous television documentaries, including in 2010 his series Chemistry: A Volatile History, which is well worth catching up on BBC, whatever it is now, iPlayer or YouTube, most possibly. And he was nominated for that for the British Academy Television Awards. And he's also been a guest on programmes like Melvyn Bragg's Start the Week, Our Time, the Today programme, and even the wonderful Infinite Monkey Cage. But tonight, he talks about strange ice. So please take it away.
Great, thank you very much, Tim. It's such a pleasure to be back. Ironically, I was only here about 2.5 weeks ago, as I came for a weekend, and then as I said, I was emotionally blackmailed by Bob, and it just seemed like a good way to raise my blood pressure, because this is our final week of full term, and there is so much marking and so much teaching and other stuff to be done. And I'm way behind, and so this is one of the things that I've learned. I mean, I operate by what's called exponential temporal discounting. In other words, if it's a month away, it doesn't even exist. If it's 2 weeks away, it barely exists. If it's a week away, it's starting to come into your consciousness. And then the day before, it's kind of and so this was kind of a good way to just heighten the suspense of things. So this evening, I thought I would come and talk to you about issues that are very dear to my heart. And over the years, I mean, I'm called an inorganic chemist, and I studied at the Inorganic Chemistry Lab in Oxford, but I've never really been able to be fully tribal. I mean, I just find all of it incredibly cool and interesting, and so I have found myself also with the attention span of a hamster moving between sort of different areas. And I lecture also to life science students and trying to convince them that chemistry is kind of a kind of bedrock subject. And don't imagine that I sort of subscribe to this idea that all biology is chemistry, because that's the same nonsense as when people say, oh, well, chemistry is just physics with knobs on. And that's kind of garbage. But it is really important for biologists to have that kind of understanding. And so there are going to be a lot of things in here which connect to these various agendas. And it is a chemistry talk, but it will morph into something quite different, which I hope will help you to kind of maybe think a little bit, maybe ask a few questions. And first of all, let me just figure out where I am. I want to show you something absolutely amazing. And for that, let me just get my camera. Oh, there we go, my camera. And you can see here this beaker, which contains one of the most marvelous materials in the universe. And you see how we're so well set up in our labs that we actually have pipework through the building, which allows you to deliver this stuff through a spigot at will. in large quantities. It's called water. And on top of that at UCL, we have devices which will allow you to cool that stuff down and turn it into a solid. Right? And here, oh, sorry about the coffee. Here it is.
Yeah.
It's called ice. Yeah. Now, ice is one of the most wonderful toys that the universe has gifted us. I think it's important throughout life to remain closely in touch with our inner 6-year-old. And first of all, you will notice that this is a strangely incontinent sort of ice. It dribbles a bit. But the best thing is, on those rare days nowadays, when it actually falls out of the sky, of course what you do is you go out and you pick it up, right? Don't you? Do you go out and grab it and you form it into this carpet may never survive. Fortunately, it looks kind of suitably hydrophobic, so that's right. And you make one of these babies, all right? And then, of course, you lock eyes with your best friends, right? And you know that moment of suspense, and then that profound pleasure that never goes away in my 60-something years experience, the pleasure of hitting your best friend in the face and seeing that look of rage, right, as you run away. Your best friend, your children, whatever. It doesn't exactly commute, because if people do it to you, well, okay. Anyway, so here it is, right? Ice. And it is, for many of us, for most of us, as we grow up, the quintessential solid, right? This encapsulates everything that we know about liquids and solids. So I want to show you what I think is one of the most extraordinary things that you will ever see in the universe. Very, very rare and unusual. So what I want to do is to take this solid, right, and safety first. I'm going to combine it with its melt. Yeah? You take it, and we're going to drop it in. What? Are you not impressed? You're not impressed? Why? I have a challenge for you. I want you to name one other molecular compound where the solid is less dense than the liquid. Come on. This is the Royal Society of Chemistry's Belgian section, right? You guys know chemistry from top to bottom, right? Name one. And everybody's shaking their head. Even the old profs, right? Right? Yeah. It's amazing. We've made. You know, if you go to what used to be Ballstein and now has some corporate name, right? There are like 3 million different compounds out there that we've made, right? Organics, inorganics, and so on. It's not normal, right? And this, to me, right, it raises profound questions, because you're sitting there going, hang on a second, I've come all the way to Tervuren to see some kind of elderly chemist show me that ice floats in water. I mean, couldn't I be at home watching Netflix? And no, but there's a really important point here. Why were you not impressed? You're not impressed because you've been brainwashed. Every single last one of you has been brainwashed. And my question to you is, who did the brainwashing? Come on, let's have some conspiracy theories. Come on, bring it up. What?
probably.
President Trump, or maybe the government, right? The government. When I do this in schools, right? Immediately it's the teachers, right? It's the teachers right there out there telling us. No, the conspiracy goes way deeper than that. Way deeper than that. I blame, who I blame? I blame the parents. Why? Well, because there's something really important here about how we learn about the world. And, when we're very small children, and if you've ever had a small child, what you see is that children are essentially doing experiments. And initially, they're just moving their arms around kind of randomly and looking, and then putting things in their mouths and finding out what's sweet and what's bitter and that kind of thing. And the way we learn is through repetition. Right? If you're going to learn how to factorize quadratic equations, God help you, right? But it's pretty essential if you're going to do, an awful lot of stuff in science or maybe even outside. You're just going to have to do it. As Eugene Wigner, the nuclear physicist, said, you never really understand maths. You just get used to it, right? And that's the point, is that so much of our kind of gut understanding of how the world works comes through this process of repetition and reinforcement through seeing things over and over again. And so when you, just to come back to my presentation, right? When your parents put ice cubes into liquids over and over again, you just gradually get used to the fact that the stuff should be at the top and not at the bottom. And then, this is interesting, because what our minds do is something really important. Remember that word induction that maybe you learned when you were studying either maths or philosophy or something? And that is this process of generalization, that if it's true for n and it's true for n plus 1, then it must be true for all values of n. And we generalize really easily. And this is an incredibly powerful way for us to learn, right? Because we can actually take individual cases, they can be repeated, and then they build up. But it's also an unbelievable flaw in our architecture. Right? When stuff kind of gets repeated enough, it becomes normalized. And you know what? You've got to be an idiot if you haven't noticed that that's how advertising works. That's how political messages work. And of course, there are certain politicians who will fixate on certain events, certain ethnic groups, individuals from them, and then generalize and say that they're all like this. And so we have to be really on our guard. And interestingly, in this weird way, I think that there is a parallel here. And we have to really be careful that when we see messages on social media, in the press, that kind of thing, because all it takes is repeating the same message enough time that gradually your sense of what is normal, how the world should be, right, shifts. Now, can I just ask, why do we put ice in our drinks? Pardon? Cool it down. Oh my God, you really are of the Uber Eats generation. I need a cold drink, right? I'm going to sort it out. I'm going to order it out. Couldn't you have put the drink in the fridge the night before, just as you did in the old days before these newfangled? Is that the reason we put the ice in our drinks? Is there another reason, perhaps? Here, the newcomers, why do you put ice in your drinks? No, you see, couldn't you have put the drink in the fridge the night before, right? If you put it in the fridge, you'd have this beautiful cold drink ready.
To keep them cold.
Yeah, absolutely, spot on. And so that's really important, is that phase transitions, processes where you melt or you boil, or you change magnetic structure, or all of those things, are places which have an associated energy cost. And so what that means is that here is your glass. You can see it's quite cool. There's a little bit of condensation on the sides, and we know the room is warm. So I want you to imagine one of those desert island programs, where they've got these hot people, right, who are standing on the beach, and they've got a drink, perhaps. Temperature 36 degrees, right? And they're drinking their mock cock, whatever tail thing, right? They're drinking. So long as you've got ice in there, the ice will melt, and of course the water, right, is going to stay at 0 degrees because the ice cannot go above 0, right? And so really what this is doing is this acting as an energy store to maintain the temperature. And I think that's quite important. So on the one hand, we've seen that ice is this outlier, and I'm going to show you some examples. But secondly, it has this great utility for us, at least, in keeping temperatures steady. And there's a huge amount of technology available to us, right? And now there are things called phase change materials, which you can put into buildings, which you can put into houses. And what they consist of are these panels. So this is something called Energain. There's another one called Micronal PCM. And what they've got are little. It's like it's like one of these wonderful structural. No, this one's actually structural. Those plastic. In the UK, everything's made out of plasterboard, and plasterboard has very little heat capacity, and so that means your house will warm up and cool down very, very quickly. Not like one of those great stone cathedrals, right? That remains really cool in the winter. And remains in the summer, and remains absolutely icy cold in the summer as well. Anyway, the thing about it is that by putting those in, the wax melts around 20 degrees, and so it kind of absorbs some of the heat effectively. And when the house cools down at night, or when the outside temperature cools down, then the wax freezes again. And what it does is, instead of your house doing this kind of thing, it really kind of steadies it. That has huge implications for energy use in buildings. And so I've actually got Energain in the roof of our kitchen or whatever. And it is remarkable in how little it moves. But that's another story. The other thing is that you can store heat. So instead of having a big hot water cylinder, you can have one of these things. This is called a Thermino, made by a company in Scotland called Sunamp. And this is in place of having a big hot water thing. What you've got is a box which is filled with sodium acetate, a hand warmer material. And what you do is once a day, you melt the whole thing, right? You take it up to about 60 degrees. And then, when you need to take a shower or something like that, you simply bring the cold water from the mains, it runs through these coils, gets heated up, and comes out at 50 degrees. What's really good is that there's no residence time. You don't have to worry about all that Legionella nonsense and so on. And it's much more compact because you can actually store a hell of a lot more energy in the melting and freezing of the sodium acetate than you do in warming up the water, all of that water to 60 degrees. So I have one of those at home, and I really like it. Also, cylinders. Cylinders don't go into cupboards very well, An enormous amount of wasted space all the way around them, right? This thing's a cuboid. This is great. You just chuck it in a corner. It weighs about a ton. But then you can put things on top of it, beside it, that sort of thing. Phase change materials. So phase changes really matter. And I think we should take a look at another ice. And so I've brought, Fabio has provided me with material for another ice. And what we've got here instead of water is one of my favorite organic liquids, toluene. It's one of the foundational molecules of glue sniffing. It's very pleasant indeed. I don't recommend it, but in the long term, but just the occasional. Anyway, let's just have a go. In fact, it was smell that got me into chemistry in the first place. It was a teacher who said to me, for qualitative organic analysis, where you had to identify the functional groups, he said, sniff it and you'll know what it is. Oh my God, it opened this whole universe. Amines were, esters, ketones, aldehyde, they were all different, right? And so, that was the beginning of the end, really. I'm still a chemist. Anyway, so what I've done is I've cooled it down to liquid nitrogen. So here is typical organic, solid at this point. It's cold. We'll talk about those clouds in a sec. But what we're going to do is we're going to do the same thing. Okay, so we're going to combine it with its liquid, and when we do that, are you ready? Here we go. Oh, Okay, well, the problem is that it's gotten stuck to the walls. So what we'll do, see if we can melt it around the edges. So watch carefully. Let me just turn this around so that we, is that, sorry, that's on the back, yeah, good. Okay, you ready? So I'm just going to touch it, just why don't we do that? Whoa! Did you see that? WTF. Right? Hang on. But I didn't put anything in there. Right? I'm just touching the bottom of the beaker. And suddenly, the liquid, can you see it? It's gone wibbly. Right? There's a wibbliness to it. Right? And the wibbliness, if you look at it, it's going down. Right? Right? And you can see it. There's clearly a motion going downwards. And what we can't see is that clearly there's got to be a whole flow like that. But we know that the toluene's at room temperature, so there's probably, what, 22, 23 in here. The toluene, the frozen solid is at minus 90 or something, minus 95. So there's clearly energy pouring from the liquid into that solid. And our solid is going to, A, warm up, but B, what we're hoping is it's going to thaw. And the wibbliness, what is that? Well, it's a convection current. What we're seeing here, right, is the fact that as the toluene cools down, its density changes. And because the molecules snuggle up closer together, the refractive index changes too. And the refractive index is an amazingly sensitive measure of temperature, of composition, of all kinds of stuff. Back in the good old days, refractive index measurements were everywhere. Anyway, what we see is a model ocean. And of course, all the great ocean currents around the world are driven by differences in density and salinity, due to temperature and salinity, right? Which move, they're the conveyor belt for energy. Let's just get our toluene-berg, into the, this is a normal solid-liquid combination. This is what they should do. Because of course, as you slow down the molecular motion, then the molecules can snuggle up closer to each other, right? And therefore the density should increase, right? And water is the outlier in this respect. And so, you can't actually see my petrol berg. No, you still can't see the petrol berg. Anyway, it's down at the bottom there, sitting happily. And of course, what it's doing now is it is taking in loads of it's going to cool down the toluene, and the thing's going to melt. And in spite of the fact that it clearly has a certain amount of air in it, right? So that's not enough. The density changes is really quite substantial. And you saw, of course, the convection current. The toluene, when we cooled it down, it got denser, and the convection current goes down. So that too is normal. Sorry, I'm just getting kind of muddled here between different. So, often people say, the molecules, I had a student who was watching this and she said acetic acid. And so I went into the lab and I took a photograph of, that's called glacial acetic acid. Back in the good old days when chemists had hair on their chests or something, temperatures in labs are so low, typically, that acetic acid, if it was pure, was a solid. And you had to chip it out of the bottle. And so they call it glacial acetic acid when it's 100%. And there it is sitting in the beaker. It melts, I think it's 16 degrees, something like that, 14 degrees. And so it sits down at the bottom. It's normal. You can also, homework. What I'd like you to do is to go into the local supermarket before temperatures warm up too much, particularly after they've reshelved things. I want you to go and take a look at the olive oil. Look at the olive oil, especially in a restaurant, if they kept the bottles of olive oil near the window. You see? Ugh, gunge. What is that? Oh, it's gone off, get the mat. No, you've been brainwashed, right? These are fat bergs. The only difference between a fat and an oil is the melting temperature. So that is olive fat, which is sitting at the bottom, as you would expect. Okay, there's a little bit which is kind of congealed at the top. But it is normal for stuff to get denser as you lower the temperature. And the more sophisticated way to talk about these things is something that sets the fear of God in most undergraduates, in fact, most lecturers and the odd professor too. And that is what's called a phase diagram. And a phase diagram is really a thermodynamic map. Okay, people get very nervous about them. What does it mean? It's a map. You're all familiar with, actually you probably aren't because it's all on your phone. But anyway, imagine you got a map and it's got coordinates, right? And there's north and south and east and west. Okay, what we've got here, first of all, is temperature. And along here we have pressure. Now the problem is that we live our lives here at one atmosphere, right? We don't get to explore the other places very much. And so our experience is kind of one-dimensional. So, here we have, let me just find it, where did the ice cubes go? I had ice cubes, but oh yeah, they are. Here are, the ice cubes that we've got from the fridge, right? And so, of course, when they're in the freezer, right, they're sort of sitting there, and what we do is we let them sit around and they warm up and eventually get to the border. And the border, well, hey, tariffs, yeah. It's called the enthalpy of melting, enthalpy of fusion. You got to pay that to go across. It's a reversible one because you get it back if you go the other way. So it's an unusual one. Certainly not Trumpian. And then you get into the liquid bit, and guess what? You go across, and then eventually you get to another border. You've got another tax, if you will, right? You've got the delta H of vaporization. So far, so good. But you notice that I've marked 0 degrees and 100 degrees. What are those? Why did I mark 0 degrees? What's 0 degrees? Say it again, louder. Freezing. Point? Does anybody see a point here? I don't see a point. There isn't a point. What's really interesting is that, here there is a point, but notice that it's on that line. And similarly, 100 degrees, we sometimes call it the boiling point. There isn't a point. It's the boiling temperature. And the interesting thing is that if you change the pressure, you're going to change that temperature. Now, I want to know, how many of you own a pressure cooker? Who owns a pressure cooker at home? 1, 2, 3. Really? I mean, you three are my people, okay? But everybody else, what? Hang on. Pressure cookers are amazing. They were invented in the 17th century. Sorry, we'll come back to that diagram in a second. By a guy called Denis Papin. He was a Frenchman who went to work in London as an instrument maker for the Royal Society. He helped build some of the kit for Robert Boyle and people like that. And he came up with this digester for bones. And it's kind of a steel thing, and that's the one that I bought. In fact, I bought in Switzerland. And you would think, what are you doing going to Switzerland to buy the most expensive? No. It was 50% off. And so at that point, it was a bargain of the top order. And what's clever about it is that you put the lid on and you clamp it down, and now you start heating it. And what happens? Well, what happens is rather interesting, because what you're going to do is you're going to travel along that curve, because the gas, the vapor, cannot escape. And so you're going to have liquid and vapor at the same time. And the pressure comes up, and so does the temperature. And so instead of cooking at 100 degrees Celsius, you're going to cook at 110 or 120. And you don't need to be much of a chemist to know the most important idea in all of chemistry. Well, one of them, which is the Arrhenius relation. As you increase the temperature, you increase the rate of reaction. So instead of cooking your chickpeas, you read the damn recipe book and it says 90 minutes. And you go, I'm not doing that. With a pressure cooker, 15 minutes, bang, you're done. Fast food, you can compete with Uber Eats, right? And this curve, the shape of this curve is really important, right? It's linked, it's defined by what's called the Clausius-Clapeyron relation, which everybody learns in thermodynamics in their first year in chemistry, physics, or science. And what it says really is that the vapor pressure of the liquid is related to the temperature by this exponential relationship, which has the enthalpy of vaporization between. And And so this curve here, this is the thing which determines whether when you go out, you're going to see blue sky or clouds, right? In fact, what we saw before, right, when I picked up that frozen time and you saw those clouds, that's interesting, and we'll come back to that. You go up into the mountains. Back in the good old days, English climbers would go up to the tops of mountains in the Alps and they would record the temperature and they would make their tea and they would record the boiling temperature, right? And that was kind of a proxy for the altitude and so on. And so there are all these amazing weather records which come from nerdy gentlemen climbers, right, who recorded this stuff all across the Alps on the top in these little notebooks. And if you're up at the South Col of Everest, right, the boiling temperature of water is below 65. And so that means you can brew up in the kettle and then just pour it straight into your mouth because it boils so low. So pressure cookers matter, but I said, clouds and so on. Well, let's think about this, because if this is true, wait a second, if the temperature goes up, you're going to be able to evaporate a lot more water from the ground. You're going to be able to dehydrate landscapes. Droughts, if the temperature goes up, are going to become that much more severe. And at the same time, if you can put much more water vapor into the sky, then that means that when the rain finally does come, guess what? You're going to get more of it. And this is exactly what we're seeing around the world, right? We're seeing that droughts across forests in North America lead to fires. Well, there was Canada. Recently, there was California. I would strongly recommend that you read an amazing book called Fire Weather about the fires in Fort McMurray about 4 years ago. A jaw-dropping book. I've forgotten the name of the author, but it'll come to me. Somalia suffered a 3-year disastrous drought where everybody's livestock died, where there was nothing for anyone to eat. And then guess what? When the drought finally broke, this is what followed. And, we often look at these pictures and we go, all those poor people, it's so tough, it's so far away. Yeah, right. Yeah, well, this is the UK. Remember those pictures of Valencia, which I forgot to put in here because I have it in the other version of the talk, right? With all the cars kind of thrown higgledy-piggledy down the road. It's coming our way. And it's nothing special, yeah? I mean, it's just this. First year undergraduate level thermodynamics, more water in the sky, or more opportunities for evaporation. So I think we should look at a different ice. Right? We've done 3 so far. And astronomers like to refer to molecular solids as ices. If you listen to the Infinite Monkey Cage, I was actually at the recording where my colleague, who I'm going to talk about in a moment, Christoph Salzmann, who is a deep expert on ice, disagreed with that view and got quite a big laugh for it. But what I want to show you is this stuff here, right? And you know what? Cunningly, I forgot to bring a proper sieve. But let me just point out that I've got it in a box, and when I tip it, hey, look. Yeah, clouds. Well, I mean, notice, of course, this stuff must be so cold that what we're doing with the water vapor in the atmosphere, because we're all exhaling little bits of moisture, is coming across there, right? And what's interesting is if we do this, let's just tip it, notice that it goes down. Yeah, it's normal. Because it's colder, PV equals nRT, right? The volume decreases and you get a convection current running downward. And by the time you're about here, right, it's warmed back up to room temperature, and so the droplets disappear. So that's kind of cool. But if I take this stuff, right, and I put it into this paper, and what we'll do is we're going to compare it. Let me just see if this is going to work. This may be just a little bit too hydrophobic, but if I take some of the regular ice, right, and I hold it in here, this may be a complete failure. Don't know whether we can see much. No, we can't see anything. All right. What I'll do is I will hold it like this. And the weird thing is that before, you saw the dribbliness, yeah? This one isn't melting. What? Come on, every child knows, right? You take a solid, you warm it up, it melts, yeah? And then you take the liquid, you warm it up, it boils, and it turns to gas. Duh. So what's wrong with this? Is this stuff strange? So therein kind of lies a tale. And this stuff, its temperature doesn't change very much. Right? This stuff has been sitting here, and the only thing that happens if I warm it up is that this little thing gets smaller and smaller and smaller. My hands get colder and colder and colder. I feel like kind of Winnie the Pooh, isn't it funny or something? Anyway, you can see it's getting smaller. Where's it going? Of course, it's going from the solid to the gas. Now, I think we should look at this, and there's a classic question, great question for students, right? How much bigger is a gas than a liquid? Right? What's the volume change? So what's the molar volume of gas? What's the molar volume of a liquid? And you can go and estimate that, and try it with water or something, use the ideal gas equation, try it out. But let's just take a look. So I've got, it's about a cubic centimeter maybe, yeah? So what I'm going to do is I'm going to put it into water, and I want you guys to count the bubbles. Okay, so we'll get a rough estimate. You ready? Struggling?
Yes.
Yeah. Okay, the ratio, somewhere around between 700 and 1,000 tons. There's a hell of a lot of gas coming off this thing, right? It's not melting, right? And you can see that it's actually got a little layer of gas right the way around it. And then the bubbles kind of detach, go up, and of course they cool the water vapor down, so of course we get clouds. Clouds is flipping wrong again. Okay, fine. So, interesting question is, how do we get the liquid? Why don't we get the liquid? Does anybody want to see the liquid? Are you up for it? What I'm going to do is I'm going to put it into a sealed container. And I'm going to let all of that gas come off. So here's the tube, okay? And you'll notice that I'm wearing safety glasses, because this is a quite dangerous thing to do. If this thing blows up, the safety glasses will be really there for sport more than anything else, because I will probably be torn apart. Pressures get quite hefty. Okay, so I'm just going to seal it up. Seal it up, and okay, so I've closed it. I want you to listen very carefully. I hope there isn't too much traffic noise, but listen. Can you hear it? So some people can hear it. Yeah, it's really interesting, because the younger people who have higher frequency hearing, right, still, whereas the rest of us, right, are completely cooked, right, you're struggling. Let me try again. Can you hear this? It's trying to get out. Okay, so let's go and see what happens. So I've got my tube, and what I'm going to do is I'm going to warm it up, and I want you to watch carefully what happens. And typically what I find is that organic things like kind of respond to affectionate handling like this. So what we'll do is just get it, just warm it up. Now watch. Can you see it? Can you see it? Okay. Try and get it against the black background if I can. Right, it's always a little tricky. But I want you to watch. Can you see the liquid now? Can everyone see it? So the question is, this is the challenge, right? Do wet, dry icebergs, do they sink or do they float? You ready? Okay, I've just got to make sure that it's there. What do you think? Sink or float? Sink. Dry ice is completely normal. It's just that we've been brainwashed into believing that it always has to melt, or let's release the pressure. Ready? So I want you to watch what happens, because when I release the pressure, you'll hear it, but you see it boils. It boils, it boils, it boils, right? If we release the pressure and listen to the amount of gas that's coming out. And in fact, there's so much gas it actually pushed it up to the top. And then the liquid's gone. It's like the best magic tricks, except that it's real. There's no sleight of hand here, right? It's amazing. How does it work? Okay, well, you know what we have to do? Remember that phase diagram business? Let's go back to it, okay? So I'm going to flip back to the phase diagram, right? But this time for CO2. And you go, it's the same thing. No, for God's sake, in this age of AI and Trump and people selling you nonsense, for God's sake, always look at the scales before you look at the data. It's really important. Notice that the scale here, 1 atmosphere is down here. Whole different ballgame. Notice that at 1 atmosphere, minus 78.5, you can go across the border from solid to gas. That's because the intermolecular forces are so weak. Right? CO2 doesn't have the hydrogen bonds, it hasn't got the dipoles, all of that stuff. And so what we did here, when I put the cap on, was, of course, there's energy flowing into it because it's cold. And so what we did was we traveled along here, right, until we got to 5.5 atmospheres. That's more than 2.5 times the pressure in a Coke bottle, right? And then we get to a point, a real point. This is called the triple point, where you have liquid, solid, and gas together. And triple points were the way in which traditionally we calibrated our temperature scales. And the interesting thing is that in the last 5-7 years, the BIPM in Paris, right, has completely redefined all of our fundamental units in terms of the fundamental constants. So they've determined fundamental constants like Boltzmann's constant, Planck's constant, and so on, to large numbers of significant figures, and then put the units on top of those. And that's actually a much more natural way of doing things, and it's giving us a much clearer view into the universe. The tragedy is that one of the key labs which has been involved in that, the NIST lab, the National Institute of Science and Technology, but their Bureau of Standards, is being basically gutted by Mr. Musk and Mr. Trump. And so the responsibility for, maintaining the foundations of our system of measurement now falls to Europe, China, Japan, and other countries, right, which have these kinds of labs. Okay, let's just come back to ice very briefly, because I want to tell you a tiny bit about some of the science that we've done at UCL. This is the structure of ice as determined by crystal structures. It's a hexagonal structure, and you can see the water molecules there. And notice that the OH is pointing towards the oxygen on the next molecule, but there's always this motif where you have one short bond and one long bond. And the interesting thing, and this goes back to Linus Pauling talking about what the hydrogen bond is that the network of these bonds and the pattern of long and short is completely random. Every crystal that you have has a different pattern all its own. And so what's weird, or what's interesting about it, is that it's a material which has highly ordered oxygens in well-established positions, but the hydrogens are kind of, they've got to be either short, long, short, or short, long, right? But you don't know where they are. And you don't know where they will be on any particular, so you have to find them. And you could have another crystal where, in fact, this one is on this side, and that one is on that side, and the whole thing shifts. So it's kind of interesting. It's disordered but ordered. And one of the questions that people have asked is, are there other forms of ice? And the person that knows more about this than I know than anyone else is this guy, Christoph Salzmann, who's a colleague of mine who works down the hall. And ice turns out to have the most complex phase diagram of any material we know. There are at least 21 different forms of ice, of which I think 19 are crystalline and 3 are amorphous. And I'll tell you about one of those amorphous ones. later. And he is responsible for finding 3 crystalline ones, plus the amorphous one that I'm going to tell you about. And the interesting thing is, we wondered whether it was possible to make an ice which was solid, but had the same structure as water. It's kind of a nuts idea. Imagine you took some water, and what you did was you just stopped everything, right? You know, like that classic game where the music stops and everybody has to do this. How would we do that? Sorry, I'll skip over that because of the time. But suddenly it occurred to me that abandoned on the top floor of our department was this device here called a cryo mill. It's a ball mill. You have these steel capsules, you put ball bearings in it. What if we put ice in there, cooled it down to liquid nitrogen temperature, and shook the hell out of it? And so we started trying to do this, and something really kind of amazing happened. As we did that, the density of the ice went up. Went up, went up, went up, until it got to 1. The same as liquid water. At the same time, the X-ray powder pattern, all of the X-ray peaks gradually disappeared. And when we warmed it back up, right, on warming, depending on how many times you'd cycled the shaking, you got a huge energy of crystallization that came out of it. And this is what is now called medium density amorphous ice. It's ice that, at least in theory, doesn't sink, but doesn't float. If you could keep it alive long enough, it'd make for the best cocktails. But it's kind of a remarkable thing, and I don't know what we do with it, but we think that what we've got is water in kind of suspended animation. And it's done essentially by taking the ice crystals and basically shearing them across until you're down to literally dust. And the structure is pretty well indistinguishable. Okay, final part of the talk, a little bit more homework. I want to tell you a book that I think everyone should read. It's a book that I was given when I was a child, written by a man called Primo Levi. It's called The Periodic Table. And my grandmother gave it to me when I was about 15, I think, or 16. I'm Italian. And so that's the cover of the copy I have. My copy, I've had it with me ever since, and it has disappeared. And I don't know where the hell it is. I'm very messy, so I don't know where. In English, Periodic Table is Sistema Periodico. And it's an amazing story. The story of a young man who goes to university in Italy in the 1930s. And he graduates from the University of Turin with their highest grade. He was top of his class in 1938. And, so he was all set for a brilliant career. If it hadn't been for the fact that in that year, Mussolini introduced racial discrimination laws. His name is Levi. He was Jewish. No employment. He set himself up as an analyst, consultant, that kind of thing, got jobs through this and that. The Second World War broke out. It was pretty disastrous. The behavior of the Italian government got worse and worse. Then the Germans arrived, and he decided he was going to be a freedom fighter, and so he went into the mountains, and he got caught almost immediately. And he was put on a cattle truck and shipped to this place, right, Auschwitz. And of the 600 people who shared the cattle truck that he was in, or the train that he was on, 6 came back to Italy. Everybody else was exterminated. And the book is amazing. And I think it's a book for our time, because there are all kinds of echoes at the moment of the stuff that was going on in the 1930s. And it's kind of a warning from history. And what it reminds us of is 2 things. First thing is he survived, and he survived because he had an education, because he was a chemist. And there's a marvelous moment when he is interviewed to be used as slave labor in the labs, and he suddenly realizes that the German officer who's interviewing him has the same undergraduate organic practical textbook that he used, Gattemann's Praxis der organischen Chemie. And that's the link that allows him to get through the interview. And he then works in the labs, he steals stuff, sells it for food, and so he survives. It's also a reminder that it could happen to anyone. Anyone. And that this stuff happens again and again and again. Please read it. And then read it again, because it's a wonderful book. Of course, I'm Italian. I go to Italy every year. We have a house in the mountains. And one year, in the valley we were in, there was an exhibition of photographs by Primo Levi. His book is divided into chapters, each named after an element. And the elements are metaphors for different periods of his life. And he used to go rock climbing as a teenager. And so there were photographs of the mountains. We have to go, let's go. So we went. And there was a photograph from 1937. The great glacier at the top of the mountain, the top of the Cogni Valley, the Ghiacciaio della Tribolazione. I said to my kids and my wife, let's hike up there. I know exactly where it is. We'll take the same photograph. Now, the weather wasn't as good, but that's the same place. And you know what's really striking? You know when you read these travel brochures or you read travel articles and people talk about going to, you don't want to go to touristy places. You want to go to the unspoiled. You want to go to the undiscovered. You want to go to these timeless places. And they're not. The Anthropocene is upon us. And there is the glacier. Just look at what's happened to that side there. To when I was a kid, it was still connected. Right? It has moved back. It used to be here in the 1930s. And that's pretty well irreversible. And this is happening everywhere. And there are huge concerns because these glaciers are the ones that provide northern Italy, Switzerland, France with water, Germany, all the way down to Romania with water all the way through the summer. What, we're going to have seasonal rivers? How are we going to deal with that? This is very serious. And the Po River is drying up every summer. The Arctic is thinning. Right? This is Professor Zach Laib. Zach Laib worked for NOAA. He was fired 2 weeks ago. Very upsetting. But you know what? We don't notice it. Why? Because in the press you get this kind of stuff. This is from a British national newspaper. Right? I won't tell you which one. Well, maybe I'll tell you if you want. Anyway, rhymes with fail. But anyway, and here's an article saying, return of Arctic ice cap as scientists predict global cooling. And look, he's even got pictures. It must be true. You know what? We have to be much more data savvy. If you see something like that, you want to say, hang on, that's just 1 year. What's the trend? Let's look at the trend. There's the trend. This is since satellite records began in 1979. You can see the trend is down. And look, it seems to have flattened out at the moment. What's going on? We don't know. But how did that guy David Rose, who was notorious for this stuff, do it? It's really simple. Every time there's a pause, right, those guys jump up and down and say, oh, look, they're alarmists. It's not happening. No, data always has noise, right? So you've got to look at the long-term trends and think about those. And you look back to 1850, and Britain was one of the great whaling countries. And they recorded where the ice was in the summer and the winter. And you can see the changes in where the edge of the ice was going all the way back there. People like Fitzroy, all those people, if you read his Dark Materials, all of the names of the characters are named after Arctic explorers of the 19th and in fact, late 18th, 19th, and early 20th century. And this is a visualization of temperature made by Ed Hawkins from the University of Reading. And we are just about here. And you can see that the temperature is gently rising. And really, what Ed is saying is we have a choice about where we go. And we can go this way. Or we can just carry on as we are and go that way. And remember what I said to you about why do you put ice in your drinks? Yeah, it's because the ice helps to keep temperature steady up in the Arctic. It's also white and it reflects light. And so, what I'm saying is the ice speaks. And suddenly I feel this this icy cold. You're all sitting there staring at me going, what do I do? Well, you know what? There's everything to play for. And for me, two of the people who have inspired me the most, I think they're absolutely wonderful. Now, these two young women here, Malala Yousafzai and Greta Thunberg, who have spoken truth to power over and over, and who have been pilloried for it or physically attacked. Remember that Malala Yousafzai was shot through the head for trying to educate women in Pakistan. And what we need to do is to talk about it, to normalize those conversations, not make it taboo. We have to vote about it. And the older we are, the bigger responsibility we have to vote in the interests of the young people, right, who are sitting at the back. Because they're more invested in this than we are. We're out of here soon. And then we need to electrify it. And we should be electrifying everything. This is my house, right? Those are the solar panels we put in 2006. That's the heat pump we put in almost 3 years ago. We've got to connect, right, the grids across Europe, Brexit or no Brexit, right? We've got to be able to link up things so that when there's excess in one place, we can shift it to another. We've got to stop burning stuff in our houses. It makes air pollution, which isn't good for us. And we go, oh, it's not a big deal. Yes, it is. We go make the measurements in some houses, it's quite hot. But with these, induction hobs are phenomenally efficient. You lose almost none of the heat. It goes straight into your pan. And they are fantastic. But I want you to look, and this is aimed particularly at the younger people here, right? At the evolution of the sizes of wind turbines, right? And look at how big these suckers have gotten, right? These are going into the North Sea at the moment. 15 megawatt monsters. They are enormous. And they are able to power huge numbers of houses. You look at Denmark, and Denmark is now almost self-sufficient in electricity. The UK has reached, there have been days when it has reached 90%, 95% entirely renewable. It is remarkable. And of course, we're going to need gas backup and so on. Look at what's happened to the cost of solar panels, right? Since they were first started being marketed in 75, they've dropped by 97%. Look at what's happened as we've increased the number of wind turbines, right? As we put in more and more wind turbines out there, what's happened to price, right? Scaling things up brings down prices. Look at the cost of batteries. They've absolutely tumbled. And you know, we have the technology now. We can do it. But the real message, I think, here, which is really important, is that this is where your jobs are likely to be. If you want the interesting, high-paying jobs, right? And it might be in science, it might be in engineering, but it might be in finance because we need to think about that stuff. It might be in data analysis. There's all kinds of possibilities, energy efficiency. These are the places to be looking at. And really, with those, you can change the world. We have a choice, and the ice speaks. Thank you very much.
Thank you very much, Andrea. I think we have time for a few questions.
Absolutely.
This might be a more general discussion around a glass of wine or two. Anyone got a quick question they want to talk to Andrea? Yeah.
I checked on your biography and I noticed that you are also expert on hydrogen storage. So what do you think about storing hydrogen as a clutterate inside the ice?
Let me say, first of all, I'm not an expert in anything, least of all hydrogen storage, okay? And hydrogen, so I got involved in that project because they kind of needed a chemist. It came out of the physics department. And so I was involved in that with some misgivings. It was really looking to see whether materials like ammonia, borane, and related things could be used, and particularly could be brought back. They have a lot of hydrogen within them, and when you heat them up, they release hydrogen. The problem is that then you get basically an insoluble white tar that converting back is a nightmare. Hydrogen, I have deep, deep misgivings about, because hydrogen is fundamentally an extension of combustion. And the fossil fuels lobby has leapt onto hydrogen because, you know what, that old phrase, when all you know is how to burn shit, everything looks like a fuel. And so hydrogen is kind of the next big thing. And at the moment, the only prospect for making hydrogen is taking methane, doing steam reforming, and getting the hydrogen out, which is what we do at the moment to make ammonia, for example. And then they say, oh, we can do carbon capture and storage. There's no evidence that that works, and certainly not at scale, right? There are nice pilot projects and so on. Hydrogen unquestionably has niche uses called chemistry, making steel potentially, although electrochemical methods are coming up pretty fast. Making ammonia, you don't have any choice, you need hydrogen for that. Again, electrochemistry may eventually come through. But I'm very, very nervous about hydrogen because I think it has cheerleaders who have other motives and who really want to continue with business as usual as long as they can. What you might want to do is go and take a look at what a guy called Michael Liebrecht, who is the founder of something called New Energy Finance, which was a consultancy set up to help people with the renewables transition. He's an interesting guy. He's very, very strongly conservative. He voted strongly in favor of Brexit and told everybody that they should do it because he hates the EU and everything it stands for. But on the other hand, I think he's a very, very clear thinker on the energy transition. He's written very well about hydrogen. And one of the things is that in the UK, certainly, people have been talking about the idea of blending hydrogen into the gas mains. Now, that's a damn fool thing to do for a very simple reason. And it's not that it's dangerous. Yeah, it is dangerous, but methane's pretty dangerous too. Yes, it embrittles pipes, but the reason is more fundamental. If you imagine you're going to make hydrogen by taking seawater, doing electrolysis, getting hydrogen out, you can do that on a good day. Let's call it 100% efficiency. The reality is probably 3/4, maybe 50% of that. Okay, you now pass it down the pipes, you deliver it, okay, you burn it. For every unit of renewable energy that you've used, you get, at best, 1 unit of renewable heat. If, on the other hand, you just get rid of the electrolyzer, you make the electricity, you pass it down the system, and you put it into a house, if your heat pump is average, you will get 3 times the heat. And if you've set up your heat pump properly, you could get 4 or even 5 times. It's a complete no-brainer, and the hydrogen thing, I think, for domestic heating is certainly the wrong direction. And heat pumps for industrial heat are coming on very fast. We're expecting to see the first Haber process heat pump, and that means temperatures of, I think, 400 quite soon. So the first pilot projects for that. So that would be my kind of rant about that. And by all means, come back to me.
Yeah.
But I'm quite nervous that hydrogen is being talked about in a way by people who have a different agenda.
Yeah. There's quite a lot of investment. There's a hydrogen pipeline, I think, put in probably Antwerp. So
big money going into it, and they are getting a lot of money from politicians. They've succeeded in getting that in the UK. They've gotten it from the EU, the US as well. Maybe that is the only thing that Trump will destroy that maybe I won't be too unhappy about, but everything else, forget it. Yes, Bob.
Well, could we take a slightly more optimistic view of ice? And could I ask you perhaps just to speculate very briefly on the biological implications for life? Because if we didn't have ice floating, there would be no aquatic life on this planet or anywhere else for that matter once things freeze.
Absolutely, and that's one of the interesting questions about the oceans of some of the outer planets of the solar system, is how you can have the solid and the liquid phase kind of coexisting. So yes, that's extremely important. The other thing is that the surfaces of ice turn out to be very, very reactive in interesting ways, and they may well have played an important role in some of the sort of origins of life kinds of things. The processes may have happened there. But of course, ice and organisms are intimately connected, and one of the most amazing things are the proteins that you have in the bloodstream of fish like Arctic char. And they're really interesting because their surfaces have evolved to essentially be able to match and stick onto the surface of ice crystals. And so what they do is they stop ice crystals growing. And that allows these fish, which have, basically fresh water in their bloodstreams, to survive in salt water in the Arctic and the Antarctic, which might be at -1, -1.5 or something. And so, the connections are incredibly intimate, and I agree. If ice didn't float, life would be probably quite different.
Everyone got a final question? Will we split for...
Ask them over a drink if you want.
Yeah, that's pretty much for it. Yeah, okay, probably.
I didn't answer your question, though. Sorry, can I just answer that? Because your question actually was whether you could store hydrogen inside ice. And that's a really interesting point. So ice, you saw the kind of structure there. It is already rather holy, wherever it is. Right? So it does have these channels. But in fact, something that was discovered by Michael Faraday is that if you take water and you saturate it with, and he first saw it with chlorine, and then it was extended to organic molecules, you can get it to freeze and to form a material which has molecules, covalent molecules, sitting inside, which are not covalently bound to the ice network. These are come to be called clathrates. And you can put methane in there, you can put ethane, propane, butane. They're really interesting. They tend to have two different cage structures. They're slightly different from theirs. There's type 1 and type 2. And these polyhedral structures turn up in silicon, expanded phases of silicon and so on. They're really interesting. People are looking to see whether those clathrates might be ways in which you could trap things like hydrogen within them. There is talk. People have successfully done it. I kind of wonder how, whether the hydrogen can't wriggle its way out. But again, if you just have a little bit of pressure there, that should be enough to stabilize it. Yeah. So it is a possibility. It is a possibility, but I just have these nervous feelings about hydrogen itself.
Yeah, strategically, so to speak.
Well, it's kind of ironic, really, that chemists should be so much against combustion, especially when it traditionally has done lots of demonstrations. I've kind of grown up blowing stuff up, and it just makes me less comfortable.
Okay. Well, thanks very much, Andreas.
Thank you.
There you go.
Oh, marvelous.
Yeah, no need to go and
wow.
buy these jocks for home.
No, it's fabulous.
There you go.
Fabulous.
Okay, well,
Thank you.
having some drinks afterwards, and right now, in fact.
Okay.
Man the bar. And our next event is on the 29th of April. Same place, same time, same channel, which we have Frank van Heek from Ghent, who will talk to us about analytical chemistry, and he's winning of the Theophilus Redwood Prize. Royal Society of Chemistry. So that's in about a month's time. So hope to see you all then. And do have a drink. Thank you. And talk to Andreas. If you want
Yes, I'm just going to
know anything about heat pumps, he's the man. Okay.
Yeah, I love my heat pumps.
He loves his.
I'm a big fan of heat pumps, and I'm
yeah?
desperately trying to stop UCL putting heat pumps in for reasons that I can explain if you're thinking of putting in a heat pump. You just need to think about it a little bit carefully and make sure your system is set up right.
Yeah. Okay. Thank you very much.